Increasing and decreasing functions. Now we can use the derivative to determine whether a function is increasing or decreasing for a given interval. So a function is said to be increasing when the gradient function is greater than or equal to 0. And a function is said to be a decreasing function when the gradient is less than or equal to 0. So if we take a look at this first curve that we have here, we can see that the gradient is always positive. If we were to draw tangents at any given point, the tangents would always be straight lines there, and they'll always be positive. So this is said to be an increasing function for all real values of x. Okay, so increasing function for all real values of x, the first one. Now, the second graph that we have here is slightly different. So what we've got here is from anything which is x value of less than -1 here, we can see this yellow highlighted part, the gradient is negative. So here it's said to be decreasing. It's also decreasing from 0 to 1 here. Then it's increasing from -1 to 0. And it's also increasing from -1 going upwards as x increases. So here it's increasing in the interval from -1 to 0, and it's decreasing in the interval of 0 to 1. And it's also increasing when x is greater than -1 and decreasing when x is less than -1. So the gradient can be used to determine when a function is increasing or when it is decreasing. Now we can differentiate a second time, getting us the second derivative. And the second derivative represents the rate of change of the gradient function. So the rate of change of the gradient function is found by differentiating twice. So when we differentiate first time, when we find dy by dx, this represents the gradient function. And when we differentiate again, the second derivative, d2y by dx squared, represents the rate of change of the gradient function. And this can then be used to determine whether we have a local maximum or minimum, or whether we have got a point of inflection. So let's take a look at how we can use this second derivative to determine the nature of the stationary point. So what we've got here is a curve, as you can see, and on this curve we've got a few things happening. We've got up here, point A is referred to as a local maximum. As you can see, the curve goes up to a maximum and then it turns back down, so referred to as a local maximum. And down here at point B, we've got something called a local minimum, because the curve goes down to a minimum value and then it goes up. It's referred to as a local since there are other points which are below this B. For instance, points around here are below that point, so that B is a local minimum. And what we have here at the origin is a case where we have a point of inflection. Now, certain things to understand here. At the local maximum, if we were to draw a tangent at that particular point, there it would be completely horizontal there, and we know that when we have a horizontal line, its gradient is 0. So at the point A, dy by dx, i.e. the gradient, is equal to 0. Likewise, at the local minimum, if we were to draw a tangent at that point, which represents the gradient there, we can then say at the local minimum, dy by dx, the gradient is also equal to 0. At the point of inflection, we can see here that the gradient is also 0. So at that point, we've got dy by dx equaling to 0. Now, what happens just before the point A? If we were to draw a tangent just before it, we can see that this tangent has a positive gradient. And if we were to draw a tangent just after it, we can see that that tangent has a negative gradient. So here, when this happens, when we have positive gradient before and then negative gradient after, this is another indication of how we can find the maximum. Notice that for a minimum, it's the opposite. So just before that, we have a negative gradient, and just after the point B, we have a positive gradient, and that's an indication of a local minimum. Now, the point of inflection is different because just before it, the gradient is negative, and just after it, the gradient is negative. Now, it could be going the other way, where you could get just before being positive and just after being positive. But when there is a sign change in the gradient before and after a point, that would indicate that it's either a maximum or minimum. If the sign remains the same as then it's a case that it's a point of inflection. So what's the second derivative got to do with this? Well, we said that the second derivative is the rate of change of the gradient. So let's investigate at the point A what's happening to the gradient. Well, the gradient just before the point A was positive, and then it went to 0. So the gradient is decreasing from a positive value to 0 and then going to negative. So the gradient's becoming more and more negative. So the rate of change of the gradient is negative. So the rate of change of the gradient is negative. How can we say that? Well, the rate of change of the gradient is written as, let's write this down, rate of change of gradient, which is d2y by dx squared. And we said that the gradient is decreasing as we go towards A and then after, therefore it's negative. So d2y by dx squared is less than 0 for a local maximum. Now, let's see what happens at the local minimum. Well, as we can see, just before the point B, the gradient is negative, then it becomes a gradient of 0 at the point B, then it becomes positive. So the gradient, the rate of change of the gradient is increasing here. So rate of change of gradient is increasing, i.e. it is positive. So d2y by dx squared is greater than 0, indicating that the rate of change of the gradient is positive here. So when that's the case, when the second derivative is greater than 0, we have a local minimum. Now, at the point of inflection, we get a rate of change which essentially it starts going from negative to 0. So it starts increasing. So just before the origin, it's negative, then it becomes 0, and then it starts. So it's increasing and then it starts decreasing here. So it's neither increasing nor decreasing. So the rate of change of the gradient at the point of inflection is 0. d2y by dx squared is 0. But that doesn't necessarily mean it is a point of inflection. We actually have to investigate and further by finding the gradient just before that point and just after to see whether they are both negative gradients, in which case it would be a point of inflection, or if they were both positive gradients, it would be a point of inflection as well. So how we might do that is by laying it out in this particular way. We might draw a table, and for a point of inflection, this is at the point, at stationary point, and this is a point which is just before the stationary point. I say just, so a small increment just before stationary point. And what we have here is a point just after stationary point. Okay, so this would be positive, 0, negative. This would be negative, 0, positive. This is negative, 0, and then negative gradient. Here it's positive gradient, 0, and then positive gradient. Okay, so we can see here what this actually makes. it makes a local maximum, a local minimum shape, point of inflection, point of inflection. So let's look at the application of this to a particular example here. Here we've got a function f of x, and we want to first of all find the coordinates of the stationary points of f of x. So I'll just do line by line maths. I'll go up to the comma and just focus on this first bit here. Find the stationary point. Now we know that at the stationary point, the gradient dy by dx is equal to 0. So to begin with, I'm going to go and find out my gradient function. Since I have what f of x is, I'm going to go and find my gradient function, which can be denoted by f dashed x, which is equal to 12x cubed minus 24x squared minus 12x plus 24. Now, we know that the gradient is 0 at stationary point, so we can then go and say 0 is equal to 12x cubed minus 24x squared minus 12x plus 24. And we want to find a value. This is a cubic here. We want to find the value of x that makes this function 0. And we can then go ahead and use factor theorem to try and find that. We've also got a function on our calculator which can be used, where we can use the equation function, and we choose a polynomial of order 3. And the coefficient of x cubed here is 12. The coefficient of x squared is minus 24. The coefficient of x is minus 12. And the constant term that we have there is 24. And then if we were to solve this, it gives us an x value of minus 1. So if we were to do x value of minus 1 actually gives us, so f dashed of minus 1 would give us 12 minus 1 cubed minus 24 minus 1 squared minus 12 minus 1 plus 24, and that would give us 0, indicating that x equals minus 1 is a solution. So therefore x equals minus 1 is one of the solutions. We can then find another solution here is x equals to 2 in a similar way. And the third solution is x is equaling to 1. So we found the x values of the stationary points, but remember we are asked to find the coordinates of the stationary points. So in order to find the coordinates, we need to then go and find the y value. The y value is the output to the function f of x, so we must go and substitute it into the f of x function, not the f dashed. Since the f dash gives us the gradient, f of x gives us the y value. So f of x is equal to 3. Let's find out what f of minus 1 is, which is going to be 3 minus 1 to the power of 4 minus 8 minus 1 to the power of 3 minus 6 minus 1 squared plus 24 minus 1 plus 20. So this then gives us 3 and plus 20 plus 8 minus 6 minus 24 plus 20. Which gives us 0. So that means minus 1, 0 is one of the stationary points. Let's go and determine another stationary point, f of 2. So if we do f of 2, we'll get 3, 2 to the power of 4 minus 8, 2 to the power of 3 minus 6, 2 squared plus 24 lots of 2 plus 20. This gives us 16 times 3, which is 48 here. And then we have minus 64. And then we have minus 24 plus 48 plus 20, which gives us 28. Therefore, the coordinate here is 228, the second stationary point. And lastly, f of 1 gets us 3 minus 8, 1 to the power of 3, minus 6, 1 to the power of 2, plus 24 lots of 1 plus 20. That gets us 3 minus 8 minus 6 plus 24 plus 20, which is 33. So here the coordinate is 1, 33. So we've got our 3 coordinates for the stationary points. We haven't completed here. We need to then go and determine the nature of each of them. Now, to determine the nature of each of the stationary point, we need to find out what the second derivative is. That will be a good way to start. So let's go and find out what the second derivative is. So for this one here, let's go and find out what the second derivative first of all is. F double dashed x, i.e. the second derivative. So if we differentiate the first derivative, we can then get what the second derivative is. So this gives us 12 times 3, which is 36x squared, minus 48x minus 12 is our second derivative. Now, what is the value of the second derivative at each of those stationary points? So at minus 1, 0, f dashed of minus 1, f double dashed of minus 1 gets us 36 minus 1 squared minus 48 minus 1 minus 12. And this gives us 36 plus 48 minus 12. So 36 plus 48 minus 12, which is equal to 72. This is greater than 0. Therefore, our second derivative greater than 0 indicates that we have a minimum at this point. We can do the same thing with this coordinate here. So the second derivative here gives us, at the point x equals to 2, 36, 2 squared minus 48, 2 minus 12, and that gives us 36 times 4 minus 48 times 2 minus 12, which gives us 36, which is again greater than 0, therefore a minimum. And if we do the same thing with the last one, substitute the 1 into the second derivative, we will get 36 lots of 1 squared minus 48 lots of 1 minus 12, and that gives us 36 minus 48 minus 12, which is equal to minus 24, which is less than 0, therefore a maximum here. The question then goes on to ask us to sketch the graph of y equals f of x. Now, when we draw a sketch, we need to consider some key points, such as where it crosses the axes, and we can also indicate where the stationary points are, and so on. So what we've got here is a polynomial of order 4. So let's go and draw our axes first and put some of these stationary points in the correct place. So drawing our axes here. So first of all, we've got -1, 0. So -1, 0. Let's indicate that is one of our stationary points. We've got 228. -1, 0 is a minimum, so it's doing something like this here. We've got 228. Suppose that's somewhere around here. Now, 228 is also a minimum. So it's doing something like that here. And then we've got 133. So 133, which is higher than 28. So there. And that's a maximum. So it's doing something like that. So we can see the shape here. It's forming already. So since this is a minimum, we'll take this up, join it there, take this down, join it down there, curve back up there. This side goes up that way there. There's our curve. We can find this intersection here. So let's just label this. This is X, this is Y. What is that point? Well, that point is when X is 0. If we substitute that into our function f of X, up there we can see that when we substitute X equals to 0 into f of X, we get to 20. So that point there is 20. So here is our sketch of f of X.